Welcome to the Deep Dive, your shortcut to being well-informed. We take complex research, break it down, and give you those clear, captivating insights. Today, we are diving into something absolutely critical for our electric future. Lithium. Specifically, how on earth are we going to get enough of it?
It's a huge question, isn't it? The demand is just skyrocketing. Think about it. By 2035, projections say over half of all new cars sold will be electric.
Wow, over half.
Yeah. And a single EV battery pack, just one, needs about 8 kilograms of lithium carbonate equivalent, roughly speaking.
8 kilograms per car. You start multiplying that out.
Exactly. You multiply that by millions and millions of vehicles, and suddenly our traditional sources, mining spodumene or extracting from those really rich salt-flat brines in South America.
The lithium triangle.
Right. They just won't be enough. We're looking at a pretty significant supply gap predicted as early as 2030.
2030, that's not far off at all.
Not far at all. So that forces us, really, to look hard at unconventional water sources. We're taking groundwaters, certain industrial wastewaters, even geothermal brines, places where lithium is present but much more diluted.
Okay, so the lithium's there, but it's harder to get out. What are the problems with the methods we have now for these trickier sources?
Well, take the classic one, solar evaporation ponds, like you see in those big salt flats.
Yeah.
I mean, it works where it works, but it needs very specific geography, arid, sunny climates. It's incredibly slow, can take months, even years.
Years. Yeah.
And it uses a lot of chemicals, consumes vast amounts of fresh water, which is often scarce in those areas. And honestly, the recovery rates aren't always that great. Plus environmental concerns.
So definitely not a universal solution. What else is in the toolbox? Maybe things like ion exchange, adsorbents.
People have definitely worked on those. And they can pull lithium out. But the big challenge, the real Achilles heel, is selectivity, specifically against sodium.
Sodium. Always the troublemaker in brain chemistry, it seems.
It really is.
Yeah.
These brines, especially the unconventional ones, often have way, way more sodium than lithium, sometimes hundreds, even thousands of times more.
Okay.
And most ion exchange resins or adsorbents, they're just not selective enough. They grab sodium too, or other ions. So you often need pre-concentration steps, which adds complexity, adds cost.
And then cleaning them, regenerating the resins, that takes more chemicals, more water.
Exactly. You need large amounts of fresh water, often acids or bases, to strip the lithium off and get the material ready again. So it's got its own environmental footprint and cost issues.
Okay. Then there's electrochemical intercalation. I've heard that mentioned. Sounds a bit like how a battery works.
It is conceptually similar, yeah.
Yeah.
Using electrode materials that selectively pull lithium ions in. And it can be quite selective for lithium, which is promising.
There's always a but.
There's always a but. The main issues there tend to be electrode lifespan. They can degrade over time. And the fact that it operates in semi-batch modes. You fill it up, extract, empty it, repeat. Not really ideal for a continuous, large-scale industrial process.
Right, you want something that just keeps running. Okay, what about membranes? Filtration membranes are used everywhere for separation. Surely they can handle lithium.
They can, up to a point. Conventional membranes, like nanofiltration or reverse osmosis, they're pretty good at separating things based on size or charge difference.
Huh.
So getting lithium Li+, separated from magnesium Mg2+, which is divalent and often larger when hydrated. Yes, membranes can do that reasonably well.
Okay.
But the absolute wall they hit is separating ions that are very similar, specifically monovalent ions, lithium versus sodium, Li+ versus Na+.
Because they're both +1 charge, similar size.
Exactly. Their hydrated sizes are very close, charge is the same. Most conventional membranes just show little to no selectivity between them. They might block both or let both pass.
And if your brine is flooded with sodium,
then you're just moving a ton of sodium around, not effectively concentrating the lithium. It becomes a non-starter for efficient direct lithium extraction from many of these sources.
Okay, this perfectly sets the stage for the core of our deep dive today. We're looking at this really fascinating study. The title is Approaching Infinite Selectivity in Membrane-Based Aqueous Lithium Extraction via Solid-State Ion Transport.
It's quite a title.
It is, and it signals a totally different approach. They're not using conventional membranes. They're using solid-state electrolytes, SSEs, the kind of materials being developed for next-gen solid-state batteries.
Yeah, taking that battery tech and pivoting its application to extraction, it's a really clever idea.
And the claim, as the title suggests, is pretty extraordinary. They report, and I'm quoting here, unparalleled performance. Specifically, lithium-ion selectivity values so high they are immeasurable by even the part per billion detection limit of mass spectrometry.
I mean, think about that. Immeasurable selectivity.
So what does that practically mean? When they say immeasurable, they literally couldn't find any other ions getting through.
That's exactly what they're saying. They set up their system, put a solution with lithium, sodium, magnesium, potassium, etc. on one side, applied a voltage, and on the other side, where the extracted ions collect. They could detect the lithium, obviously, but using highly sensitive mass spectrometry, capable of finding parts per billion, they found 0 detectable traces of the competing ions like sodium or magnesium.
Wow. That's fundamentally different from anything else we've discussed.
It really is a complete step change, potentially.
So how does the specific material they used, it's a Nasicon type SSE, lithium titanium phosphate but doped with other elements like germanium, aluminum, or silicon, how does it achieve this seemingly impossible feat?
Okay, so there are a couple of key things about this Nasicon material. First, it has high lithium-ion conductivity. That's why it's interesting for batteries, right?
Yeah.
Lithium ions can move through its crystal structure relatively easily.
Okay, conducts lithium well. Makes sense.
Second, and this is crucial for this application, this specific type of Nasicon is remarkably stable in water. Many solid-state electrolytes just fall apart or react when you put them in contact with aqueous solutions.
Right. That wouldn't work very well then.
Not at all. So finding one that's stable is a big deal. But the real magic, the secret to that incredible selectivity, is the mechanism. It's what they call anhydrous hopping.
Anhydrous hopping. Okay, break that down. Anhydrous meaning without water.
Exactly. No water involved in the transport through the membrane itself. See, in conventional membranes, ions usually move through water-filled pores or channels. They keep their hydration shells, those little clusters of water molecules that surround ions in solution.
Mm-hmm.
But this Nasicon material, it's a dense, rigid, crystalline solid. It's completely impermeable to water molecules themselves. So for a lithium ion to get through, it first has to be stripped bare. It has to shed its hydration shell entirely at the surface.
Okay, so it goes in naked, basically.
Basically, it becomes a bare lithium ion. And then, driven by an electric field you apply across the membrane, it hops. It physically jumps from one specific vacant site to another within the solid crystal lattice of the Nasicon.
Like moving through a series of atomic-scale docking stations inside the crystal.
That's a great way to put it. It's solid-state diffusion. And because it's happening inside this tightly packed, precisely structured crystal, the material can be incredibly picky about which ions can make that journey. It's like an atomic-scale sieve or, like you said earlier, maybe a very exclusive nightclub.
Huh. Okay, so who's the bouncer at this atomic nightclub? What determines who gets in? Is it just size?
Size is a huge part of it. The study talks about the specific structure of these Nasicon materials. They have these conduction channels, these pathways for the ions, but they have very narrow bottlenecks.
How narrow?
They estimate the critical size, the tightest squeeze point, is between about 1.8 and 2.0 angstroms. Extremely tiny. Now, a bare lithium ion, the Y+, has a crystallographic radius that's small enough to just fit through that bottleneck. But a bare sodium ion, Ne+, which is the next most similar competitor, it's just slightly larger.
Large enough to not fit.
Large enough that it's effectively blocked. It's physically too big to squeeze through that 1.8 to 2.0 A gap. So size exclusion is the primary bouncer keeping sodium out.
Okay, that explains the lithium versus sodium selectivity. What about other common ions like magnesium, Mg2+? Sometimes divalent ions can be smaller than monovalent ones, right?
They can be in terms of their bare ionic radius.
Yeah.
But magnesium runs into other problems. It's about charge exclusion and energetics.
How so?
Firstly, getting a doubly charged ion like Mg2+ into the lattice site designed for a singly charged Li+ creates charge imbalances. There's an energetic penalty associated with creating the necessary defects in the crystal structure to accommodate that higher charge. Secondly, magnesium ions have a much higher hydration energy than lithium.
Meaning it takes more energy to strip off their water shell.
Exactly. They hold on to their water molecules much more tightly. So the initial step of getting dehydrated at the membrane surface is much harder for magnesium. Combine the difficulty of dehydration with the energetic cost of entering the lattice, and divalent ions like magnesium are effectively barred from entry too, even if their bare size might seem okay.
So it's a combination of size and charge and the energy needed to shed water. It's multi-factor security.
Precisely. It's this unique combination enabled by the solid-state transport mechanism that leads to that immeasurable selectivity they observed. No detectable sodium, potassium, magnesium crossing over.
That is genuinely remarkable. But you hinted earlier, or the outline did, about a trade-off. Even if these other ions can't get through the membrane, their presence can still cause issues.
Ah, yes. That's a really important practical point. So the selectivity is essentially perfect zero permeation of competitors. But the rate at which lithium ions cross the membrane, the lithium flux, can be affected by what else is in the solution.
How does that work if they aren't going through?
They basically crowd the entrance. Imagine our exclusive nightclub again. Even if the wrong people can't get past the bouncer, if there's a huge mob of them blocking the doorway, the eligible guests, the lithium ions, have a harder time getting to the entrance and going inside.
Okay, so it's surface site blocking.
Exactly. It's a surface phenomenon.
Yeah.
The study confirmed this using techniques like SEM-EDs, which looks at surface composition, and XRD, which looks at the crystal structure. They found, for instance, that sodium ions can kind of integrate or absorb onto the surface layers of the nasicon membrane, especially at high concentrations.
But not penetrate deeper.
Correct. They sit on the surface, potentially blocking the active sites where lithium needs to enter the lattice to begin its journey. So higher concentrations of sodium or magnesium in the feed solution lead to a lower lithium flux, even though the selectivity remains perfect.
That makes sense. And what about protons, hydrogen ions, H plus H, especially if the solution is acidic, low pH?
Protons are actually an even bigger challenge in some ways. Unlike sodium or magnesium, protons can sometimes migrate through certain SSE lattices, including nasicon types, especially at low pH.
So they can get past the bouncer?
They sort of can, yes. They're very small and mobile. This means they can compete directly with lithium ions for transport pathways within the membrane, severely reducing the lithium flux and potentially impacting the overall efficiency and purity. Managing pH seems quite critical.
Okay, so surface blocking from competitors and potential competition from protons inside the membrane. These are engineering challenges to address, but the core selectivity is still there.
Absolutely. The core mechanism is sound, but optimizing the interface, managing the feed water chemistry, especially pH, will be key for real-world application.
Got it. So let's zoom out. We have this incredibly selective membrane technology. What's the big picture implication? Why is this potentially so much better than, say, advanced nanofiltration for lithium extraction?
The killer advantage really comes down to energy efficiency. Think about pressure-driven membrane processes like nanofiltration or reverse osmosis. You spend a lot of energy just pushing vast quantities of water through the membrane pores.
Right, most of what you're moving is water, not the lithium you actually want.
Precisely. It's inherently inefficient from an energy perspective when dealing with dilute solutions. But with this electrochemical SSE approach, you're applying an electric field to selectively drive only the lithium ions across. You're not wasting energy moving bulk water.
Okay, so the specific energy consumption, the energy needed per kilogram of lithium extracted could be much, much lower.
Orders of magnitude lower, potentially, compared to pressure-driven methods for achieving similar separation goals, especially from dilute sources. That's what makes it so promising for making direct lithium extraction from these unconventional resources economically viable and, importantly, more sustainable.
Wow, okay, that is a powerful advantage. Less energy means lower cost and a better environmental footprint. What an insightful deep dive this has been. We've really unpacked how these solid-state electrolytes could offer a truly radical solution to this looming lithium crunch.
Absolutely. I think the big aha moment for me, and hopefully for you listening, is grasping how fundamentally different this mechanism is. Forcing ions to shed their water shells and navigate this precise, dry, solid lattice. That's the key.
Yeah, that anhydrous hopping, creating near-perfect size and charge sieving, it moves us way beyond the limitations of conventional water-filled membrane pores, especially for separating similar ions like lithium and sodium.
Exactly. And we also got into that crucial trade-off, didn't we?
Yeah.
So that even with perfect selectivity, you still have to manage the crowd at the door, the surface blocking by competing ions, and especially the challenge posed by protons at low pH.
Right. It's not magic. There are still engineering challenges, but the potential is undeniable, especially that energy efficiency advantage you mentioned.
Definitely. Lower energy use is a massive driver for any new separation technology, aiming for sustainability and economic feasibility.
So as we wrap up, let's leave our listeners with something to think about, a provocative thought for the future. This study focused on lithium, obviously, because that's the immediate huge demand. But does this principle, this idea of using highly selective solid-state ion conductors, Does it stop at lithium?
That's the exciting question, isn't it? I mean, the principles demonstrated here achieving extreme selectivity through solid-state transport through precise lattice control could potentially be applied much more broadly.
You mean designing other solid-state materials tailored to selectively transport other critical elements?
Why not? Imagine developing bespoke solid-state ion conductors for efficiently extracting, say, rare earth elements from industrial wastewater, or maybe cobalt or other valuable metals currently locked away in complex dilute aqueous mixtures where conventional methods struggle.
That opens up a whole new frontier in resource recovery and critical materials science.
It really does. Of course, there's a lot of research needed. As the study implies, we need to understand the limits are their conditions, like very high voltages or extreme concentrations, where this infinite selectivity breaks down. We definitely need more water-stable SSE materials beyond NASACON. And, as we discussed, optimizing that membrane solution interface to minimize blocking and maximize flux is paramount.
Absolutely. Lots of work ahead. But it sparks the imagination. So the final thought for you is, what other vital elements, currently difficult or uneconomic to extract from water sources, might we unlock using this kind of tailored solid-state ion transport? The potential impact could be enormous.